This is the reason a piece of silicon sitting on your roof can power your refrigerator, your lights, and your phone, without a single moving part, without any fuel, and without making a sound. Solar panels create electricity through a process called the photovoltaic effect, and the science behind it is stranger and more interesting than most people realize. Here is exactly how it works. The story opens in 1839, when a French scientist named Alexandre Edmond Becquerel first observed that sunlight hitting certain metal plates produced a small voltage. Nobody had a practical use for it, and the observation sat largely dormant for over a century. Charles Fritz built the first attempt at a usable solar cell from selenium in the 1880s, and it converted less than 1% of sunlight into electricity, far too weak to power anything meaningful. That ceiling held until April 25, 1954, when Bell Laboratories in Murray Hill, New Jersey changed the picture entirely. Daryl Chapin, Calvin Fuller, and Gerald Pearson had been researching silicon semiconductors when an experiment with gallium-doped silicon treated in a lithium bath produced something nobody planned for: a significant electrical current when held up to sunlight. Pearson connected wires to the material, pointed it at the sun, and recorded what became the first practical silicon solar cell in history. Bell executives unveiled what they called the Bell solar cell to the public, using only sunlight to operate a 21-inch Ferris wheel, and that 6% efficiency figure became the starting line for everything that followed. The New York Times covered it on the front page, calling it the beginning of a new era, the harnessing of the almost limitless energy of the sun. Nokia Bell Labs, the modern successor to the original laboratory, still lists the solar cell among its greatest innovations, and in 2008, all three inventors were posthumously inducted into the U.S. National Inventors Hall of Fame. Sunlight is not just brightness. Composed of photons, massless particles of electromagnetic radiation carrying energy that varies by wavelength, it delivers billions of these particles to every surface around you every second, most of which pass through or bounce off without doing anything useful. That changes when photons hit silicon. As the semiconductor material found in 90 to 95% of all solar panels, silicon occupies an unusual position. It conducts electricity under the right conditions but not others, which meant engineers could design around its behavior. On its own, plain silicon absorbs very little. What makes a solar cell work is what manufacturers do to the silicon before it ever sees sunlight through a chemical process called doping. Each solar cell contains 2 layers of silicon treated with different elements. Phosphorus infuses the top layer with extra electrons, giving it a negative charge, while boron strips electrons from the bottom layer, creating a positive charge. Where those 2 layers press against each other, a p-n junction forms, a built-in electric field that sits there permanently, waiting. And that's when the photons come in. They knock electrons loose from the silicon atoms, electrons that would otherwise drift randomly, and the electric field at the junction forces them to move in a single direction. Conductive metal strips running across the cell collect that directed movement and channel it into wires, which carry it out of the panel as electricity. A single cell produces very little on its own, which is why a standard residential panel groups either 60 or 72 of these cells together, combining their output into enough power to actually do something. Most explanations of solar panels stop at the cell, but the electricity leaving those panels cannot go directly into your home. What solar cells produce is direct current, electrons flowing steadily in one direction, and almost every appliance in your house runs on alternating current, where electrons reverse direction many times per second. The power grid delivers alternating current too. Direct current from a panel plugged straight into a home would power nothing. What bridges that gap is a device called an inverter, and every solar installation includes one. The inverter takes the DC electricity streaming in from the panels, processes it, and outputs AC electricity that the home's electrical system distributes normally. From there it reaches outlets, appliances, and anything else drawing power, and if the panels are generating more than the home needs at that moment, the excess flows back into the grid. 6% was the number Chapin, Fuller, and Pearson started with in 1954, and tracing what happened to that figure over the following decades tells most of the story of modern solar. Hoffman Electronics pushed the number to 14% by 1960, more than double the original in just 6 years. Commercial panels averaged below 10% through the mid-1980s, climbed to around 15% by 2015, and the best commercially available panels today are approaching 25%. In a laboratory setting in May 2022, Fraunhofer YSE in Germany recorded 47.6% efficiency using a specialized 4-junction solar cell, a design that remains outside standard commercial production. What actually happens every time sunlight hits a solar panel runs from photons knocking electrons loose from silicon atoms, to an electric field forcing those electrons into a current, to an inverter converting that current from direct to alternating, to electricity reaching every outlet in the building. No fuel consumed, no emissions produced, no moving parts involved. That entire chain of events traces back to an accidental experiment in New Jersey in 1954, when Gerald Pearson held a piece of doped silicon up to sunlight and recorded something nobody expected. 70 years of refinement later, the technology that grew from that accident now adds nearly a gigawatt of new capacity to the world every single day. The next time a solar panel comes into view on a rooftop, that is what is running inside it.